All right, so vertex animation is today's topic, and it's not just the topic of today's lesson, it's going to be the topic of this whole unit that we're now entering. But because this is the first lesson, let's start off with a quick intro for this topic, and then we'll get into what's the project that we're going to work on today that's going to hopefully sell you on some of the cool things we can do with vertex animation. So first, let's just do this intro. Let's cover a couple key questions here. First of all, what do I mean by saying vertex animation? We're going to create a custom displacement in our vertex shader. So that's going to be very similar to what we did in the previous lesson with our trick shadow, where we were not just sort of applying a matrix transformation to the entire model. We were going in vertex by vertex, and we were changing what displacement was hitting each vertex depending on like what the vector to the light was, or from the light. So that was one example of a custom like per vertex displacement. For animation, we're going to do this, and it's going to vary by time. So whether that's just a linear time thing, or there's some type of interaction or state change of a behavior that's happening over time, but this is going to change over time, and that's what's going to lead to this being animation. All right, so then why would we do this? And in particular, why would we do this versus like skeletal or traditional animation that you would see in a game? You'd also see this called like rigged animation. Basically, the idea is that we have bones, a hierarchy of bones. Each vertex is weighted to a collection of bones, and then there's a skinning process where those vertices kind of conform to the bone positions, and that actually typically will happen on the GPU, but in a vertex shader. But before that happens, you're manipulating the bones directly on a CPU. So why would we do vertex animation instead of this traditional type of animation? One big reason is just the type of animation. Certain things are just going to be much easier to do with vertex animation, like cloth or water, right? So you could, theoretically come up with like control points that are bones and kind of manipulate those control points, but you'd rather sort of manipulate or animate this entire surface. Another key reason is performance, and we talked a little bit about performance last time. It's going to be a bigger and bigger topic as the course goes on, but the basic idea here, as I mentioned, that this skeletal animation, usually, not always, but usually it's happening on the CPU, okay? Whether that's an animation that you're bringing in from some external program, or you could be doing like IK, inverse kinematics, physics type animation, or even manipulating these bones in a script, but it's all happening on the CPU. And basically the reason that can cause a performance bottleneck is that animation data or animation state needs to be transferred to the GPU in order to render the animated model. Well, what happens there is, let's say we have many different elements that are going to be animated, but even if they share the same mesh, we can't just efficiently dispatch that draw call to draw all of those elements that have all these custom animations on them. We're going to have to, between each iteration of that draw, we're going to have to come in and change some kind of state. It's just going to be a much more efficient, performance-wise, to be doing animation on the GPU, where we can just issue these simple commands very quickly from the CPU and then let the GPU kind of get to work on the animation. And final reason why, which we're going to be looking at a lot today, though it's not necessarily totally a feature of vertex animation per se, but it's more just procedural animation, is that we can do a lot of variation inside of a procedural animation, which by definition, a vertex animation is going to be procedural in some way. So that's kind of my overview of vertex animation. We're not going to spend a ton of time on the whiteboard up front. We may come back a little bit here or there throughout the lesson, but just to give you an overview of what we're going to be doing quickly before we head into Unity and start doing it, is we're going to animate, drum roll please, a blade of grass. Okay, so we'll start with the blade of grass. Let's see, we may not end up with the single blade of grass though, but to start off with, let's do a blade of grass. And to do that, we're just going to start with our trusty tube, and we're going to turn this into a blade of grass. So what we want to do is create some type of sort of cool breeze that's blowing this blade of grass around. I mean, it's going to be taller than that, but I just sort of drew this as the base mesh we'll be working with. Now, before we do that though, let's have to make a quick change to the way that we're generating this mesh. Remember, we never actually embedded our UV texture coordinates into this, so although it already has them ready to go, we just need to embed these because we want to perform some of this animation with this V coordinate specifically embedded into this mesh. So that being said, let's get to work on our grass animation. Okay, so I've set this up ahead of time. I copied out our previous scene and kind of made some color changes here. We see we have this kind of dirt ground and our sky, and we've got also a grass material ready to go with a custom shader. So I just duplicated out this PFX lit surface into a grass shader because we're going to be doing special stuff inside of the Vertex shader here, and I assigned it to this material. But we don't have our actual grass mesh yet. And let's actually create first like a parent object that's just called grass, and then underneath that we'll call it blade, is the single blade of grass. So let's add our tube. It's already highlighted there. And actually, before we do that, let's make the changes to the tube, because I also want to make some change to this tube that will make adding that script a little bit nicer, which was, let's go back in and fix our error from lesson 1 where I just skipped over this. So we're not going to need to do this. Actually, I kind of like to do this. So let's add these attributes to require a mesh filter and mesh renderer. That will just cut down our setup a little bit since we're already making changes to the tube. And we come down here to where we actually build the mesh. We're going to need to add our texture coordinates here. So let's add a list here, and we'll call it text chords, and this is going to be a vector2 list. And then come down here and make sure that we, once this is populated, which we will do in a second, but we'll just make sure we set it on the mesh. You set it with this UV property here, and we'll say text chords to array. Okay. Now we'll come up here, and just whenever we're adding our vertex to the vertex, they call it vertices. I mean, it's really these are the positions, and then we'll add our texture coordinate. I mean, I say that because the texture coordinate and the position's kind of all part of the vertex in my sort of rhetoric or frame of understanding. But whatever, this is the way Unity has it set up. So we'll say text chords.add, and then we already have our UV calculated there. So okay, that should work. So let's come back into the editor, and let's take our blade and let's add our tube to it, and now we should get our mesh filter and mesh renderer. Great. Let's assign this grass material, and now let's reset this radius curve thing. All right, let's build the mesh. Okay, so we've got the mesh here. Remember, it doesn't have a cap, but that's not going to be a problem yet, so let's keep ignoring that until we have to do something about it. So we've got our tube. I think it looks like a weird shape, but I think let's actually leave this for now because we'll be doing a lot of this sculpting in the Vertex shader itself, almost as part of the animation. So I think we need fewer U subdivisions because this is not really like a very circular object. It's going to be more of like a flat blade of grass. And then the V subdivisions, let's just add something a lot so that we have some room for some animation here. So we'll build our mesh. Okay, there. I don't know what happened with that flickering there, but it's there, ready to go. Okay, so we've got our scene set up. Let's just save that for good measure. All right, and now let's split screen with our code, and let's open up that shader. Okay, right off the bat, I'm seeing before we really get into the grass shader, let's just make one change here, which is that we're going straight from object space to screen space, and we can't do that in this because we're going to be manipulating these positions. So let's go from this world space position to our screen space, which we did in our trick shadow. Let's just copy what we did in that over to our grass shader. And so we'll be taking this world space position into screen space. But beyond that, let's also do something where we'll create our own local variable here called object space position. And we'll start off by copying this. And so we'll use this sort of locally declared object space as the input to our transformation to world space. Right now it's going to do the exact same thing. If we compile, come over here, it's doing the exact same thing, but we're going to want to sort of manipulate this object space position before we take it to world space. And then before we take this to screen space, we may want to do some additional manipulation there. Okay, so let's start doing this. Like, what am I talking about? Right now, this is like a weird shape. So what we can say is like blade height equals, let's say 5. And then we can multiply the object space y by our blade height. And we should see now, right, that sort of has grown there. So let's say that's like a decent height for our blade of grass. And so it still looks kind of like, we kind of want this to be flatter than this. So we can take our object space z coordinate and let's multiply that by like 0.25. So that basically what we're saying is that we're going to have kind of like a wide shape, but then on the z-axis, it's going to be narrow. So we've got this kind of flat blade of grass now. I actually kind of don't mind the fact that it has this missing cap at this point because it is kind of more like this flat blade. But what we could do though is still apply some type of tapering up at the top. And so what we could say is our object space xz, we can multiply by the v texture coordinate. Remember, the v coordinate is starting at 0 at the base and goes up to 1 at the top. So we can say our in.uv.y is our multiple here, and let's see what happens. It doesn't compile because we need to bring in our uv coordinate, even though we added it to the mesh. And let's see, make sure this actually works. Bring this into the shader. So we'll say uv, and then we'll give it this semantic text chord 0, and that should bring that over from our mesh if we set that up correctly. Okay, and we'll see here we need to do the inverse of this, right? Because this goes from 0 to 1, so if we want to add a tapering, we can say 1 minus, and then we'll have the full width at the base. Come over here. Okay, so that's doing a very aggressive, like linear taper, okay? And even if we don't want to go down to a single point, we'll still see this like linear shape. So let's say like min taper width is 0.5, and then what we can do is you can say 1 minus this coordinate value times the min taper width, so that will go to a minimum value of 0.5. 1 minus 0.5 is 0.5, right? But we still see this like linear fall off to this now. And so what we're going to do here is go back to our whiteboard, and I think this is the only time we're going to go back to the whiteboard here, honestly, but I think it's worth illustrating this concept, which is exponential easing, because I use this all the time in all kinds of things, really. I just haven't used it yet in this course, and you may be familiar with this concept already, but if you're not, the basic idea is that we start with a value that's within our 0 to 1 range, like our UV coordinate is, and this is really like a magical range. This is kind of one of the reasons why I always like to keep things in that 0 to 1 range that we use to drive our parametric functions, because if you just map a value that's going from 0 to 1, kind of like that, and you say, here's our input to a function, and here's going to be the output to the function, this is kind of if you do nothing to it, you just leave it be. It's just going to be like this linear line. Like we saw, our taper has a linear fall off. And if we want to do an easing to it, what we can say is we can just take the power of our input by some type of ease pow. And basically what that's going to do is we're going to have something that looks kind of like this, which is like an exponential growth curve. But the key factor to this is that the start and end, so long as we have something in this 0 to 1 range, this is really important. If we have that, this will have the exact same range in the input space as the output space. Say if we have 2 as our ease power, so we're kind of like squaring this value, right? 0 is going to go to 0. 0 times 0 equals 0. 1 times 1 equals 1. But 0.5 times 0.5 does not equal 0.5, it equals 0.25. And then 0.25 times 0.25, I believe, is going to be like 0.0625. So you can see that that's what creates this sort of exponential growth, is that we don't linearly increase this output as we linearly increase the input. It's an exponential increase. And the higher that we go with this ease power, we'll basically do the same thing. So if we wanted to do it to the third power, then 0.5 would be 0.5 times 0.5 times 0.5 again. So it would be even more hugging this lower bound. Okay, so the higher we go with this ease pow, the longer it takes to ease in. Before we get back to the example, let's just do another simple version of this, which is the ease out version. We're going to do something that's very similar. This is going to be 1 minus pow, 1 minus in, and then raise that to our ease power. Now, why does this work? Because we're going to take 1 minus in, which is going to give us this shape, right? So when we're 0, we'll get 1. When we're 1, we'll get 0. And then at 0.5, we'll get 0.5, okay? So that's going to give us this inner portion, and maybe we can draw in colors here, right? This is going to give us this part. Now if we take this power part, okay, we've seen what that's going to do, except on this input shape. So if we figure out what that's going to look like here, it's going to be hugging that 0 bound again, and it's going to create exponential growth, except it's going in the opposite direction. Okay, so then let's circle that in this color. And then the final part is the outer part is that we're going to go 1 minus again. And hopefully you can visualize what this is going to look like. That's going to flip the y-axis again. And so we'll get something that looks like that. And so that's going to be our ease out function. So let's add these into our shader code. And we can go split screen on these. And so we can just declare these functions up here. We can say ease in of our value is going to be, take a power. And I mean, this is going to be identical to just saying that, right? Okay, and then we say but just for simplicity of reading the code, we'll add these. And then this one would be a little bit more handy. We can do that, okay? So we've got ease in, ease out. Now, is there an ease in out? Maybe we'll get to that in another lesson, but we'll stick to these two for this lesson. So, okay, so our min taper width is here. And just to make sure this is working, let's just reduce our min taper width so we can really see it. And this is kind of a counterintuitive way that we've written this. So why don't we kind of change this a little bit? So let's just say we'll go down to a minimum of 0.25, and then we'll get our taper t, which will be kind of the controller of this taper. We'll say that's just going to be our UV texture coordinate. We'll try to not do it so inverted this time. And then we'll ease this out by our taper pow, let's say, and we'll declare a taper pow. Let's just use 2. And then we'll take our object space position xz and multiply it by lerp from 1 down to our min taper width. And we'll use our taper t to control that. So let's see what that looks like. Okay, I mean, kind of cool, but I think we are using the wrong easing function, right? Because in our case, our start value is where it's wider. So we want to ease in towards this narrower thing. So let's ease in towards the min taper width of 0.25, and we'll see there, okay, that's kind of like what we're looking for. Now what we can do is even increase this so that it's even more extreme of an easing. Could go even further, right? And then we could also like increase this or decrease it even to 0. And so you can see how that's working now. So I think this is looking okay. I think it's looking kind of like a wide base. So maybe we could just multiply in just kind of like a overall width equals 0.5 or something like that. Like multiply that in, right? But you could spend forever tinkering with this. Okay, this looks pretty good. So we've got kind of our blade of grass now. So I think what we want to do now is add some kind of animation where, let's say, here's the positive x direction. Let's say we want to have this sort of bend in the positive x direction as this breeze is coming through. So here's where we're going to bring in our time-based motion. So we can say our breeze amount is going to be, we can use a sine wave, And let's pass in this thing called time.y. And again, I can link to the built-in Unity variables. This is one of them. The .y part is giving us the seconds. So this is just a running counter of the time. And so we can multiply in some kind of like breeze speed here. Let's just say 2. Let's see what that looks like. And let's transform this to a 0 to 1 range, right? Remember, sine gives us -1 to 1. And so we want to just transform that to 0 to 1 so we can do all of our tricks with it. And then we've got our breeze amount. So now what we can do is we can say object space dot x plus equals breeze amount. And we can say breeze amplitude equals 1. And let's actually rename our breeze amount to breeze t. That shows this is kind of like the parameter that's controlling it. And then this amplitude is going to be the actual displacement amount that's going to be applied when we have the maximum breeze t parameter. Okay, so we can see what that looks like. That's not exactly what I had in mind because it's moving the entire blade of grass. So again, you can see we just want to apply this as the blade of grass is going up from the base. We don't want to apply it to the base. And so what we can say is breeze mask equals we can do another one of these easing functions. Let's start with just the, without the easing. We can use our texture coordinate to mask that. And then we can remember to multiply in our mask. And so now we're getting this blade of grass kind of swaying like that. Okay, but I mean, again, we're seeing this linear motion, right? So let's try to add some kind of mask to this that's more interesting. So again, we can do like an ease in, I think, on this one. And what does that look like? Okay, so now we can see that this is sort of having more of a curve to it there, to the shape that's being applied. And then let's slow this breeze down because I'm thinking that this should be sort of more of a like very slow breeze that's coming in and out. And then what we can do is we can add a flutter to this that's more of a faster displacement. So what we can say is down here, our flutter speed is going to be much faster, like let's say 15. And so then our flutter t, we can multiply that in. And then we can do something similar here and just change this to flutter. And then we'll take our flutter t, just replace all these, and let's see what that looks like. Okay, so obviously the flutter, as I was describing it, should have a lower amplitude than this breeze that's going to be moving it more. Okay, so that's a little bit more like what I had in mind. I think the breeze amplitude might want to be more than that. And then this flutter, I think is pretty good. I think it could even be faster, like 20, let's say. And then what I think could be cool as well is if we take this breeze t, remember this goes from 0 to 1, and what we could do is we could multiply our flutter t by our breeze t so that way we only see this flutter when there is a breeze. Okay, so there's a breeze currently, then it comes in, then it's still. And it might be nice actually if we see a little bit of that flutter even when there's no breeze, but not, right? So if we could do something like that, that will say that there's like 50% constant flutter, and then we're adding in 50% of the flutter is contingent on this breeze being there. So then like, what's that look like? Okay, so I think we could even, be more, sort of just have just a tiny bit of the flutter when we're sort of more at rest there. Okay, so I think that's pretty good, but right now we're just working on a single blade of grass, right? So what happens here if we start copying these out and we start populating like a field of grass, right? Okay, so far it looks okay, I guess. Now what happens if I start rotating these around though? And let me just start also, I'm going to start adding random rotations to these various blades of grass. Okay. and you can start to see there's a kind of a problem there, is that they're tilting in all these different directions. And actually, let me start really being aggressive with my copying and start sort of systematically populating a field of these blades of grass. So we've kind of created like a field of grass now, and you can see there's a couple of problems here. One is that they're all moving in exact unison, right? And they all look like the exact same blade of grass, except they've been rotated around, so they're not even blowing in the correct direction. And this flutter especially looks ridiculous that it's all moving in unison. It almost looks like stop motion because of that. But let's get them pointing in the right direction first. So what we can say is this aspect of it we can do after our object space transformation. So we can bring stuff into world space first, and then we'll apply our breeze and flutter into our world space X rather than our object space X. So let's just see what that looks like. Okay, so now they're at least pointing in the right direction, and we've got a little bit of variation because of just these random rotations that I applied to each blade of grass, but otherwise it still looks obviously like the exact same blade of grass. So now what we can do though is we can start adding some variation to some of these variables. So like flutter speed, for example, let's start playing around with different flutter speeds. So we can say this is going to be, let's go between, let's say 15 and 25 using some kind of flutter seed. Now, what's the flutter seed? Right now we have no way of generating like a random number, because remember, we can't access the system random number generator from a shader. We're going to have to generate a pseudo-random number inside of our shader. And how are we going to seed that so that we get the same seed per blade of grass? Okay, because we don't want this to be changing from frame to frame for the same blade of grass. Otherwise, this animation is going to be skipping all over the place, right? We want a constant seed per blade of grass for this particular variable. Okay, so what we'll do is, well, I still have this transformation to screen space that we later override, so let's remove that. But where it says here, world space position, what we can say is up at the top here, let's track our world space origin. So rather than multiplying our vertex into world space, let's do just the origin into our world space. And what that's going to do is for each blade of grass, there's going to be a single world space origin for all of the different vertices along this one blade of grass. So this world space origin is going to give us a unique sort of value per blade of grass, and then we can use that world space origin in order to generate some type of pseudo-random value. Okay, so what we can do is, let's say we're going to use two input variables for our grass random, or we can just call it random value, and then we'll take two different inputs to that, and then what we can do is we can just take a sine wave. We can multiply x by some very large number, and what that's going to do is we're going to sort of try to not detect that this is actually on some wave. We just want to get some sort of totally random looking value out of this sine wave, and then what we can do is add in a sine of our y and do kind of the same thing with some other value. Okay, and then we can multiply that by some other value just so that we make sure we take that over the number of repetitions that the sine wave has, and then we'll transform that to our favored 0 to 1 range. Okay, so that's our random value function. So let's create our seed with that. So we'll say random value, and then we'll pass in our world space origin x and our world space origin .z. And so let's see, we've got everything else in place. Let's see how that works. Okay, and so you can see that these blades of grass now, the breeze part is still working sort of all in unison, but these various flutter animations are now desynced with each other. And that actually is starting to look pretty decent. Now the next thing I'm noticing here is every single blade of grass is still the exact same thing, right? It's still all the exact same height, same width, everything. So if we come in here, let's start by doing the same thing with our taper width even. So we could go from, like, let's say 0 even to up to 0.5, and we can say our taper seed is going here, And then for our taper seed, we want to give it a different seed than our flutter seed. Just we want to keep layering in as many different sort of layers of different variation on top of each other to reduce this impression that they're all the exact same object. So the more layers of different seeds that we add, the better. So in this case, what we can do is just add some kind of multiplier. Again, just go with something that's kind of random feeling so that we get a different value out of this seed thing. And so here, remember, we have to call this a taper seed. Whoops. And so let's see what that does now. Okay, so we can see, is that changing? Yeah, we can see this one went down to a single point, whereas some of them are more of like this broad thing. We could actually even say like that's like 0.75 to really exaggerate the differences there. So some of these are more kind of broad blades of grass, and some kind of come down to more of a point. Okay, now what we could also do is take this blade height and do the same thing here. So we could say, excuse the weird keystrokes there. We could say lerp between, let's say, 2 and 5 with our length seed. We'll just call it len seed. And then we'll do the same thing here. And we'll add a different value here. Okay. And let's see what that does. Okay, so I mean that maybe is a little bit too extreme. There's some really short and stubby grasses now, so maybe let's bring that up to like 3. And then maybe we can do the same thing with our overall width, or we could call this base width. We could go maybe from 0.25 to 0.75. And let's make sure that we're multiplying that in there rather than overall width. And then we can say our width seed is going to have some other sort of totally random thing assigned to it. And it didn't like that because we never put our width seed in here. Okay, so that's a little bit too much. Let's dial that back. Let's say between 0.4 and I think 0.5 is a good maximum. So we could say like that, 325. That's a nicer number. Okay, I mean it's starting to look a little thin now because our blades of grass are smaller. So maybe we could come in and multiply these again. And I should also mention as I'm doing this, this is not necessarily what I was talking about as far as optimized, right? These are all, first of all, these are sort of heavy meshes that we made just for this example, but also these are still individual draws. Now, I don't know whether Unity is going to go in and have some kind of batching that they use with the current setup. They have different batching methods they use. But at the very least, there's no different animation information that needs to be set on these things. They're all using the exact same like material, and that's where the animation's coming from. So there's fewer state changes at least that we're getting here, but we'll get much more into the optimization stuff as this course progresses. We're not really touching on that yet. Okay, so we can see our field of grass here is looking decent. I think what we could also do is, rather than have this breeze hit this field uniformly, what if we have almost waves of wind coming through this? Okay, so to do that, what we can just say is our breeze T, we can like subtract out, we can use this world space origin that we already created, and we can just subtract out some type of, let's say, world space origin.x, and then we'll say breeze frequency. Okay, so we can say breeze frequency, and we don't really want to add like variation to this because this is an effect that we want to affect the entire field of grass, right? So we can say our breeze frequency, let's say, is 0.125. Let's see how that works. Okay, so I can see what it's doing, but this is kind of very slowly coming across here, right? And so I think what might make this look even cooler than what it's doing currently, which kind of looks cool, it doesn't look that realistic. What if we make this breeze T, after we transform it to this 0 to 1 range here, what if we then do a ease on this? So we can say breeze t equals ease in, let's say, I would like to find a way to use that ease out. We haven't used it yet. Okay. And then we'll try that. So now you can really see that this is moving through, right? I think it's still too slow. So what we can say is we can increase the speed, right? And now we're seeing this wave that's going through our grass. And now because this is so sort of eye-catching, I'm not really seeing the flutter too much anymore. So I think the flutter might need to be expanded here. Flutter amplitude. So let's increase our flutter amplitude and see if that makes it look any better. Okay, we could even push that further. Okay, let's see what that looks like. So you can see now that's starting to look like an interesting sort of grass effect. Okay, and so I think that's about what I wanted to cover in today's lesson. I mean, obviously you could keep tweaking this till the cows come home, and that is kind of part of the fun of this job, is to keep tweaking these effects. Now, I think what could be cool with this as well is adding some kind of interaction to it, kind of like we did with the light, color, or position. We could create like a shader global that we have some object that we're moving around and displacing this grass, and we could come up with a way to do it where it almost looks like that effect kind of sticks around for a little while before it reverts back to the neutral position. But I think the idea has been kind of communicated here. Here are some techniques generally that we want to use inside of Vertex animation. Here's some ways that we can create variation within that. And see, now I'm looking at this, man, there's too much flutter when it's neutral now, right? So now I want to come back here and say, let's reduce this neutral amount even further. But, you know, now I'm starting to really noodle, which I just said we shouldn't do. So anyway, I think this is a good place to wrap this lesson. Let's come back and we're going to start doing some more sort of complex character style animations in the next lesson.